Hello everyone, welcome to Neso Academy. We are learning theory of computation, and in the previous lecture, we have already completed our discussion on deterministic finite automata. And now in this lecture, that is Introduction to NFA, we are going to begin with our new topic, that is non-deterministic finite automata. So let's see all the topics of this lecture. Our first topic is Introduction to NFA, and our second topic is Five-tuple representation of NFA. So let's get started with our very first topic, that is Introduction to NFA. I hope you all remember the classification of finite automata. I have told you that finite automata or finite state machines have various types, out of which we have already completed deterministic finite automata. Now we are going to begin with the second type of finite automata, which is NFA, non-deterministic finite automata. Do you remember this example? This is a transition diagram of DFA. I have taken this example when I was explaining you deterministic finite automata. And there I have told you that this is an example of valid DFA. Why? Because this diagram satisfies all the properties of deterministic finite automata. For every current state, there should only be one next state for the given input symbol. Every state should have a transition for every input symbol, and there is no null transition in this diagram. That is why it is a valid DFA. Now, what if I remove few transitions from this diagram? Also, if I replace this symbol B from the input symbol A, is it still a DFA? Of course not. This is not a DFA because it now violates all the properties of DFA. But this diagram is called as non-deterministic finite automata. Why? Because now you can see for the current state Q0, there are more than one next states possible for the same input symbol A. Also, here you can see it is not necessary that every state should have a transition for every input symbol. Q0 has a transition for A, but it doesn't have a transition for B. Q1 has a transition for B, but it doesn't have a transition for A. Q2 has a transition for A, but it doesn't have a transition for B. So this is a non-deterministic behavior, and that is why this diagram is called as a non-deterministic finite automata. I hope a basic intuition behind NFA is clear now. Now we will understand NFA formally. NFA or NDFA stands for non-deterministic finite automata, which I have already told you that the full form of NFA or NDFA is non-deterministic finite automata. NFA is a finite automata in which the transitions from one state to another state can be non-deterministic. That is, for a current state and a given input symbol, more than one next state may be possible. Let's understand this point. NFA is a finite automata, which I have already told you that NFA is an example of finite automata without output, in which the transitions from one state to another state can be non-deterministic, which means that in NFA, the transitions or movements from one state to another state can be non-deterministic, or we can say can be not unique. For an example, if there is a transition from state Q0 to Q1 on input symbol A, and there is one more transition from Q0 to Q2 on input symbol A, this is a non-deterministic behavior because we are getting more than one next state for the current state Q0 on the same input symbol A. This was not allowed in DFA, but it is totally allowed in NFA because NFA allows the non-deterministic or not unique transitions. And in NFA, for a current state and a given input symbol, more than one next state may be possible, which I have already told you. For a current state and a given input symbol, more than one next states are possible. Now let's see the next point. It is not necessary in NFA that each state has a transition for each input symbol. It was necessary in DFA that every state should have a transition for every input symbol. But in NFA, it is not necessary that every state should have a transition for every input symbol. Like here you can see, Q0 has a transition for A, but it doesn't have a transition for B. Similarly, Q1 and Q2 don't have transitions for A as well as B, but still it is a valid NFA. If I add few more transitions, then also it will still remain as a valid NFA. Null move or epsilon as an input symbol is allowed only in a special type of NFA called as epsilon NFA. Now, if you remember, while explaining DFA, I have told you that in DFA, every transition should be triggered by an input symbol. And similarly in NFA also, every transition should be caused by an input symbol from the alphabet. There cannot be any epsilon transition or a null move in a regular NFA. But it is to be noted that there is a special type of NFA called as epsilon NFA, in which null move or epsilon as an input symbol is allowed. So in regular NFA and DFA it is not allowed, but in a special type of NFA that is called as epsilon NFA, it is allowed. Epsilon NFA is the third type of finite automata which we will study later. So I hope you have understood all these points. Now let's see a few diagrams and find out whether they are NFA or not. Here is the first diagram. In this diagram you can see Q0 has a transition for A and B, but Q1 and Q2 don't have the transition for A and B. So it is not a deterministic finite automata, but it is definitely a valid NFA. Why? Because in NFA, it is not necessary that every state should have a transition for every input symbol. Let's see the next diagram. In this case, you can see for the current state Q0, there are more than one next state for the same input symbol A, which is a non-deterministic behavior, and it is not allowed in DFA, but it is definitely allowed in NFA. So it is also a valid example of NFA. Let's see the third example. In this diagram, you can see there is an epsilon transition or a null move, which is not allowed in DFA as well as it is not allowed in NFA. So this is neither a DFA nor an NFA, but it is an epsilon NFA that we will study in our upcoming lectures. Let's see the last diagram. In this diagram, you can see all the transitions are complete, and this is a valid example of a deterministic finite automata. And here you need to note down one very important point. Every DFA is an NFA. That means this is also an example of NFA. So every deterministic finite automata is also a non-deterministic finite automata. But every non-deterministic finite automata is not necessarily a deterministic finite automata. I hope you have understood all these examples. In this way, we have completed our very first topic, that is Introduction to NFA. Now we are going to proceed with our second topic, that is Five-tuple representation of NFA. So while explaining DFA, I have told you that DFA is an ordered collection of 5 elements, and that is why it is called as five-tuple. Similarly, NFA is also an ordered collection of 5 elements, and that is why it is also called as a five-tuple. This is the five-tuple representation of NFA. So the 5 elements of NFA are Q, sigma, delta, Q0, and F. Let's understand these 5 elements one by one. Q is the finite and non-empty set of states. Sigma is the input alphabet, which is basically the set of input symbols. Delta is the transition function, which is the collection of transition rules. This is the equation of delta. Delta, which is Q cross sigma, is giving us 2 to the power Q. We will understand this equation in a while. Q0 is the initial state of an NFA, and F is the set of all the final states of an NFA. That means there can be multiple final states in an NFA like DFA. So these are the 5 elements of an NFA, and these 5 elements are used to completely define an NFA. Now we will find the values of each of these elements with respect to the given transition diagram of an NFA. So here I have taken an example of a transition diagram of NFA, and we will find the values of all of these elements with respect to this particular diagram. So our first element is Q, which is finite and non-empty set of states. Or we can simply say Q is the set of states. In this diagram we can see there are only 3 states, Q0, Q1 and Q2. So Q is the set of these 3 states, Q0, Q1 and Q2. Second element is sigma, which is the input alphabet, or we can say the set of input symbols. In this diagram you can see there are only 2 input symbols, A and B. So sigma is the set of only 2 input symbols, A and B. Now the third element is transition function, which is delta. I have told you multiple times that transition function is the collection of transition rules, and transition rules are the rules that determine what will be the next state on the basis of the current state and the current input symbol. This is the way of representation of transition rule. This Q is the current state, this sigma is the input symbol, and 2 to the power Q represents the set of next states. Why the set of next states? Because in case of NFA, we can have multiple next states. That is why we have the set of next states. If you remember, in case of DFA, here we were only having Q. Because in DFA, there is only one next state possible. But in case of NFA, there can be multiple next states, and that is why we have the set of next states. Now let's take an example from this diagram. You can see Q0 on A gives Q0, and Q0 on A also gives Q1. So if the current state is Q0 and the input symbol is A, there are 2 next states possible, Q0 as well as Q1. So let's write it. If the current state is Q0 and the input symbol is A, then the next states can be Q0 as well as Q1. So this is a way of representation of a transition rule in an NFA. And in this way we can write all the transition rules for a given NFA. Here you can see Q0 on A gives Q0 and Q1, which you have already seen. Q0 on B gives Q2. Q0 on B gives Q2. Q1 on A gives Q1. Q1 on A gives Q1. And Q1 on B also gives Q1. Q1 on B also gives Q1. Q2 on A gives Q0 and Q1. Q2 on A gives Q0 as well as Q1. Q2 on B gives a null set. In this diagram you can see there is no transition for the state Q2 for the input symbol B. That is why we are getting the null state. And this is totally possible in an NFA. There can be a state which don't have any transition for any input symbol. So this is valid in case of NFA. And sometimes we will get the null set for the given transition. Now we will understand the meaning of 2 to the power Q in detail. 2 to the power Q means the power set of Q. And the power set of Q means the set of all the subsets of Q. Here we have the set Q, which contains only 3 elements, Q0, Q1 and Q2. So the power set of Q will contain total of 2 to the power Q, that is 2 to the power 3 elements. So the power set of Q will contain total 8 elements. Let's verify with this diagram. Suppose you are at the state Q0 in this NFA. And for now, let's ignore all these transitions. You have to tell me how many next states are possible from the current state Q0. So if you are on the current state Q0, the next state can be only Q0, the next state can be only Q1, the next state can be only Q2. The next state can be the set of Q0 Q1, Q1 Q2, Q0 Q2. And the next state can also be the set of Q0 Q1 and Q2. And we have just seen The next state can also be a null set. So there are total 8 possible next states for the current state Q0. That is represented using this 2 to the power Q. In this way, we have completely understood transition function. Now let's proceed to the fourth element, which is initial state Q0. In this diagram, you can see Q0 is the initial state. So the value of Q0 is Q0. F is the set of final states. In this diagram, you can see Q2 is the only final state, and that is why F contains only one element, which is Q2. So I hope you have understood the 5-tuple representation of an NFA. In this way, we have completed our second topic also, which is 5-tuple representation of NFA. So this was all from my side for this lecture. Thank you, and I'll see you in the next lecture.